All right, so last time we started section 9.2, and just a reminder of where we left off. We were talking about multistage experiments. We talked about the fact that we're going to have tree diagrams on most of what we do, and if not a tree diagram, some other form of some other form of work. And I'll show you another example of that today too. All of our tree diagrams that we're working in section 9.2 will be at least 2 stages, if not more. We talked about the fact that every time you're working along a tree diagram, the actual branch that you're working along, you multiply along the branches. And I mentioned it, but kind of in passing last time, that if you needed to, like 2 branches actually fit the criterion, you would take what you got as you multiplied them and you would add their results together. So that's something that we didn't actually end up needing to do, but I spoke about it very briefly. We'll do it again today. We mentioned independent events and the fact that they get confused sometimes with mutually exclusive events, which we talked about in section 9.1. Remember, independent events means that when the outcome of one doesn't affect the outcome of another, like rolling a die and tossing a coin. Those don't affect each other. Mutually exclusive means the events have nothing in common. So when you're talking about mutually exclusive, for example, if you were rolling a die and you get an even, and you're rolling a die and getting an odd, those are mutually exclusive events. But if you were to roll a die and get a 2, and you were to roll a die and get evens, those would not be mutually exclusive. But that's something slightly different than independent events. And then we did a few examples. This one was the last one we did last time, where it didn't have a tree diagram, but our work was the equivalent of doing a tree diagram, just displayed differently. So this is the one we're on at this point. We're taking a look at a spinner. Example 3 says, suppose an experiment consists of spinning the first spinner, followed by the second spinner. Find the following sample space. Now, we mentioned sample space back in 9.1. At least you watched it on the video that I posted from that particular class period. Sample space means that you're just writing a list of all the outcomes that are possible. So you can do that in a tree diagram. This one you can actually do in a little bit nicer of a way, I think, anyway. And so I'm going to show you what that might look like. So we're going to do some curly braces to represent that these are the collection of all the items that are going to be coming next. And one possibility is that I spin the first spinner and I get a 1. So I could spin the first spinner and get a 1, and then the second spinner and get a 1. And so this kind of looks like an ordered pair, right? So this was the outcome 1, 1. Does it have to be written that way? No, you could write it as just a 1 and a 1 without the parentheses, but I don't want you to look at this later and say, hey, why did I write the number 11? So I'm going to write it like an ordered pair. Another possibility is you could have spun a 1 and then spun a 2. That's a second possibility. We're just writing out all the possibilities. So what's my last possibility if I spin a 1? 1, 3. Now, it's probably important to note that as my spinners are given specifically, they're done in such a way that they're divided very nicely, right? The first spinner is 50-50. It's equally likely to land on a 1 as it is to land on a 2. The second spinner, at least visually speaking, we're assuming, and it is the case, that it's equally likely to land on the 1, 2, or the 3. So we're going to use that fact here in a moment. But maybe I don't actually spin a 1 first. Maybe I spin a 2 first, and then a 1. Or a 2, and then a 2, or a 2, and then a 3. And those are the only possibilities. I've listed everything possible on the first spinner combined with every distinct possibility on the second spinner. There are only 6 different outcomes, okay? So we have some questions then that follow. Mine's on the next page. Yours is on the same one. And it wants to know the probability of spinning these different events. So if I had done this in a tree diagram, I could have done it like this. I could have done a 1 and then a 2, and then I could have done like this, right? 1, 2, 3. And if I did, they would actually end up with equal probabilities along all branches, because this one was a 50-50. I had a 1/2 probability here and a 1/3 here, right? So 50-50 on the first branches, and then 1/3, 1/3, 1/3. So each of these has a 1/6 probability, because we would multiply, right? I'm not going to finish filling in this tree diagram, but what I want you to see is there are 6 possibilities here, yes? So the idea that there are actually 6 possibilities here actually plays into, and it works out here because they're all equally likely. It doesn't always happen. Our example where we were selecting the names out of the hat for people going to Hawaii, that didn't happen on that one. So it wouldn't work like this. You couldn't just list all the possibilities and say, oh, they're equally likely. It doesn't work. But it does on this particular one. So if we're wanting to know the probability of spinning 2 even numbers, we can go over here and we can find any of the options that have 2 even numbers. And what options do you see that fit that category? Just the one that's 2, 2, right? There's only one possibility out of 6 that that's ever going to happen with this particular diagram. The second one says spinning at least 1, 2. So if we go back over here and we look for all of those possibilities, we're going to look for everything that has at least 1, 2 in it. And those are all of them, I believe. That's 4. So we have 4 of them that have at least 1, 2 out of 6. What should I do? I should reduce, right? We're going to reduce when we can. So this actually reduces to 2/3. Very good. And the last one says exactly 1, 2. So there's one of them, namely this one right here, that has 2 2s, and all the other one of them have just 1 2 in them. So when we're looking at spinning exactly 1 2, that would be 3 of the options out of 6 that are possible, which reduces to, 1/2. So any questions on that? So on this one, if you had wanted to do your tree diagram, you definitely could have. It wouldn't have been bad or anything like that. It would have definitely been a possibility. We could have on the previous one as well. But I think it's kind of nice to see that when things are equally likely, there's other options besides tree diagrams that are still showing our work and fleshing out the details. Okay. Okay, so interestingly enough, we went to dinner last night with a couple from our church who has a 3-year-old. She's almost 4. We were talking about stains on shirts, and I talked about this exact example. And I told her it's been around in my toolbox of examples for a really long time. So when I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears the shirt. I'm sure that that was estimate low. There's got to be a higher estimate for that for reals. If the shirt is stained, there's a 0.2 probability that I will not be able to adequately remove the stain, right? Like it's going to stay stained forever. Y'all know what that looks like, right? It continues to be stained all the time, yeah. So the question is, what is the probability that my son's new shirt will be permanently stained after the first time he wears it? So I wanted to show you this example in particular because this is a place where you don't necessarily have to do a tree diagram that has equal distribution of branches. So over here, we had, 2 sets of branches. There's 2 branches, and then there's 3 off of the 3, right? Over here, we had one that we did. It was much more detailed, and it was 2, and then there were sets of 2, and then there was all these sets of 2. It all looks very symmetric, right? Well, your tree diagrams don't always look symmetric. So for this one in particular, it wouldn't make sense. So the first thing that's happening is that when my son wears the shirt, he either stains it or he doesn't, right? Those are the 2 possibilities. So he stains it, or there's no stain. You could put the word doesn't if you want to. That would be fine. Now, if he doesn't stain it, that's the bottom branch, I don't need to spot treat the stain, right? Okay, I mean, like it's not going to happen. There's an example that you're going to do when you do your homework where you're drawing letters out of a box, and it wants you to figure out, like, if I draw 3 letters, what's the probability that I'm going to spell the word hat? Well, if I don't draw an H on the first time, I'm done. There's no hat coming out of the box, right? So keep that in mind. Keep this problem in mind when you see that example, is that doesn't necessarily mean I have to show all the possibilities. It's either I draw an H or I don't. Right? He either stains it or he doesn't. It doesn't have to be all possible outcomes. So it says in the problem that there's a 0.15% chance, or 0.15 chance probability that he stains it. So what is the probability then that he doesn't? Yeah, 0.85. So I also did this example because I wanted you to see one using decimals instead of fractions. The one we did last time had fractions in it. Okay, so if there's no stain, we're good to go. We put the shirt back through the laundry, it's all good. But if there is a stain, at least hopefully we stain treat it so that it doesn't come through permanently. So if we stain treat it, we have 2 options. Either the stain comes out, or I'm just going to say it doesn't, right? It is permanently stained. All right, so there's a 0.2 in the problem here. Where does that 0.2 go along these branches? What one?
Where it comes out.
Where it what?
Comes out.
Where the stain comes out?
Yeah.
Careful.
I think it's
Yeah, so we want to be careful. It actually says there's a 0.2 probability that I won't be able to remove the stain, so the stain doesn't come out. So this is the 0.2 down here. 0.2 probability that I cannot get the stain out of the shirt. So what's the probability that I do get the stain out of the shirt? Yeah, 0.8. Now notice, I drew the true diagram, which means every branch that I did draw does have a probability on it. That is going to be happening regardless of what happens otherwise. We're going to flesh out all those details. Now the question that I'm supposed to be answering is, what is the probability that his shirt will be permanently stained after the first time he wears it? So where is that on this picture? Well, it says it's going to get stained, and then what's going to happen? It doesn't come out. This is the branch that it's referencing. Does that make sense? Okay, so how can I use that branch then to find the probability it's asking me for? Yeah, we would multiply along that branch. So I have 0.15 times 0.2, and what would I get? 0.03. So that's equivalent to a 3% chance. It's a 0.03 probability that when he wears it, it is permanently stained the first time. That's got to be a low estimate. There's no way that's right. But anyway. Okay. So that gives you an idea about how to approach a problem where all the branches are not equal. What happens doesn't necessarily mean that it does or doesn't. Like it says it does not adequately come out. So it doesn't say like, well, maybe it comes out partly, or maybe it doesn't come out at all. Like there's other things that this is not a black and white situation, but the way the question's asked is very black and white. Does that make sense? Okay. All right, another example. I sort of alluded to this one last time. We talked about probability of genders of children. So Joe says if a family has 2 children, the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 probabilities, the probability of having 2 boys is 1/3. Is Joe correct? Explain. So first of all, he's thinking of the problem kind of like we did the problem over here, right? There's 3 outcomes, boy, boy, girl, girl, 1 of each. But there's a problem in what he's done. Does anybody know what it is? His problem is he's assuming things are equally likely. Do you remember when I did this problem, I said I could do this, and it was okay because each of these outcomes are equally likely. It's a 50-50 kind of thing. Well, it doesn't quite work out that way in this particular situation. So we're going to draw a tree diagram, and I'll show you why. So Joe and his wife, they have child number 1, right? And there are 2 choices, a boy or a girl. And along each of those branches, what should I write? What are my probabilities? They're 50-50. So you can use decimals or you can use fractions. It doesn't matter to me. I'm going to use decimals on this one, 0.5. That's baby number 1. Child number 2. We have another possibility of boy, girl. And what's going to go as the probabilities along each branch? Y'all don't want to talk to me today, do you? 0.5. Thank you, Brooke. This is not a trick question, I promise. I'm not trying to trick you. 0.5. It's 0.5s. Yeah. Okay, so do you see that at the very end of each branch, I ended up with 4 outcomes? There's outcome 1. I have outcome 2. I have outcome 3. Can you see that green? Barely. Okay. And I have outcome 4. How many outcomes are there? There are 4 outcomes. There are not 3 outcomes like Joe is sort of proposing, I guess, in the way that he says it. What has he sort of not thought about when he's made his claim?
The order.
Yeah, he's not thought about the order. Right? One outcome is having a boy and then a girl. Another outcome is having a girl and then a boy. Those are 2 different outcomes. Yes, they both result in, having a family that has 1 of each, but those outcomes are different. So if you multiply along each of these branches, 0.5 times 0.5 is what?
0.25.
Yeah, 0.25. You can also see that, again, it's each a 0.25 or a 1/4 probability of each one of those different 4 outcomes happening. Okay, does that make sense? So when it says, what would we say to Joe, or explain what Joe's issues are, his incorrect reasoning, the idea is something like this. So Joe is incorrect. Because there are 4 ways to have 2 kids. Let's say 2 children. If we were to try to do kind of like we did over here, I'll flip back here in just a second, I promise. Kind of like I did over here where I just listed the outcomes. We could do it that way. It's that the outcomes would look more like this. Boy, 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 girl, girl, boy, and girl, girl. A space. Let me make that a little smaller. Right, those are the 4 outcomes, actually. Hence, the probability of having boy, boy, which is what he was claiming, is not 1/3. It's actually 1/4. Does that make sense? And there's lots of things that we could think of like that. You can think about like tossing coins, right? It's 50-50 each time. Yep, KK, I mean, AK.
How do you know from the question that it's asking about order?
Because he wants the probability of having different outcomes, and the outcomes he's sort of lumping together are the boy-girl and the girl-boy outcomes. And so you have to sort of look at what the outcomes look like. That's what's going on there. And he's also assuming that they're equally likely, and you need to be really careful assuming that they're equally likely. You're going to encounter, I don't want to spoil it, but you're going to encounter another question in your homework where you need to think very critically. I mean, just because there's 2 outcomes doesn't mean it's equally likely chance of those things happening. So you need to be really careful when you're thinking about outcomes, because the number of outcomes doesn't necessarily relate to the probability of those outcomes, right? It rains or it snows. Well, those aren't the only outcomes, but also just because it has those 2 outcomes doesn't mean that they're equally likely, right? There's other things playing into it. So be careful when you're looking at that. Okay, any other questions on this one? Okay, the next example is my family example, real life stuff. You ready? Okay. Huntington's disease. Have any of you heard of Huntington's disease? I see some nodding and some nodding yeses and nos. Huntington's disease runs in my family. So Huntington's disease affects your central nervous system. What it does is it overproduces, I think it's an enzyme. Remember, I don't teach science. An enzyme that actually gets in the way of your central nervous system processing movements correctly. So it will get in the way of you being able to have control over balance or have control over stopping. Like, so think about like the time it takes your brain to tell your foot to stop in the car. It slows that down. Your ability to swallow, your brain to tell your throat what you're doing. Okay, so that's what Huntington's does. It's a progressively worse disease. And the age of onset of the disease, we'll talk more about statistics in our next chapter, but the age of onset of disease is the average of your parents' age of onset, but the standard deviation is 18 years. So that is a huge standard deviation. We'll come back to that idea when we look at this in the next second. That's huge. So if your parents started having symptoms at age 50, then you have a 68% chance that you'll have symptoms within 18 years earlier to 18 years later of that age. It's huge. So this disease actually runs in my family. My grandmother had Huntington's disease, and so did my father. So in 2001, my parents decided that they're going to tell us that this is part of our lives. Part of Thanksgiving, actually. Yeah, not joking. So I was married at the time. I'd been married for 3 years. My sister had been married for 1 year, and my brother was seriously dating the woman that he is married to now. Like, they were just really young at the time. So the probability that a child will have Huntington's disease if their parent has it, so that would have been my dad, is actually a 0.5 probability, much like the last problem that we did, 0.5 chance. So my dad have it, it's 50-50 chance that I have it, 50-50 chance that my brother has it, 50-50 chance that my sister has it. And so we were actually living out of state when my parents, popped the big news on us, so to speak, that Thanksgiving. And so we were staying in their home with them when they did that. And what I'm about to show you next is kind of what I did. I didn't do a tree diagram in my brain, but it's the mathematics that I did once they shared that news with us. So I do have 2 siblings. I'm the oldest, so this first branch is actually me. And there are 2 possibilities. There's the possibility that I have it, or I don't. Right? And it's equally likely, which means each branch is actually also a 0.5 probability. So my sister, she's the next one. So this next set of branches represents my sister, and she again also either has it or she doesn't. How did I write before? Have, don't. I'll say have, don't again. Same for my brother. Now my verbs are all wrong, but you can pretend with me for a moment. Have and don't. So that's my sister. All 50% probabilities. So 0.5s along all the branches. My brother is the baby who's like 6 inches taller than me. Either has it or he doesn't. Have or don't. Sometimes people feel like, I can't make my diagrams look, you just spread them out. The longer you make those lines, the more space you end up having. So if you're feeling like things are cramped, it's probably because your lines are not long enough. So make longer lines. Oh my goodness, how many 0.5s do we have? A whole bunch of them, right? Okay, so I sat there after this information was shared with us that evening, and in my mind, I sat there thinking, one of us probably has it, right? Like, look at all these places where it says have. I mean, like, one of us probably has it. And so what I sat there thinking is, what's the likelihood that at least one of us has it? And that's the first question that's asked on the next page. What is the probability that at least one of the 3 of us, of me, my brother, my sister, has Huntington's disease? So if you go along these branches, every branch that says somebody has it, so this whole top piece is all taken out completely, right? Because I have it if I'm on that branch. The second branch is taken up because the one right here has it. And the third branch, the next one right underneath it as well, because the middle child, that would be my sister, would have it. And then the last branch is taken on the very top, that at least one person has it. So if the question is how many of us actually, or what is the probability that at least one of us has it, the only piece that actually doesn't satisfy that criterion is the very last column. Do you see that? So this is kind of like our question where we were sending the people on the trip to Hawaii, right? The only one that didn't satisfy the criterion that we were asked for was the very last branch when we looked at the second question. So when we're looking at this, we could actually calculate every single one of those branches. We could do that, and this one wouldn't be too bad because they're all the same, right? 0.5, 0.5, 0.5. We'd have that added together multiple times after we multiplied them together, and we could do that. But there's actually an easier way to do it. We can actually take 1 minus the probability that none of us do. None of us has it. And that's my last branch. 1, 2, 3, none of us has it. And what would the probability along that branch be? You're right, Emma. If I multiply along that branch is 0.5 times 0.5 times 0.5. That is actually 0.125. And if I subtract those, I have 0.875. So I sat there in my old bedroom, my parents' house, and I didn't do a tree diagram, but I did those numbers in my head, and I knew that one of us has to have it. I mean, like, seriously, look at these numbers. This is really high. It's like, I mean, if somebody told you you had a 90% chance of having something, you would be like, count me in. I'm pretty sure I'm going to have it then, right? Well, this isn't just me, it's my family, but 90% chance basically of Huntington's progressing to the next generation. And so that night, my husband and I made the decision right then and there that I'd get tested. So the reason my parents actually decided at that point to share the news, they had known since 1995 that my dad had Huntington's. So they'd known for 6 years and didn't tell anybody. And the reason that they shared the news when they did was because there was new advances in technology. And so those new advances in technology involve in vitro fertilization, where you can grow an embryo to 8 cells, I think that's right, and then you can take one of the, I'm not getting all the language right, don't go tell your biology teacher on me, okay? Anyway, you can test the embryo at that size, and you can tell whether it has the Huntington gene. The Huntington gene is a gene, everybody has it, and it's just whether or not you have enough triplet repeat counts of the A's and T's and B's, and B's not a letter, A's and T's and, I can't remember, whatever. G and C, there we go. And if it's got enough of those, then you actually get this disease. You show symptoms and so forth. So anyway, you can basically then decide whether or not to use that embryo in vitro fertilization. And then you, of course, have to make decisions about what to do with the embryos that test positive. And my husband and I said, we can't do that. We weren't comfortable. We felt like that was too much playing God, and we weren't willing to do that. And so we made the decision right then and there that if I tested positive for Huntington's, that we weren't having kids. It wasn't going to happen. And so actually, that was the day that my husband and I first started talking about adoption. So, as you know, we have adopted children. But you may also know that we have a biological child. So it took us a couple of years. Wow, I slipped too far away. And I was tested, and I do not have Huntington's disease. So we waited for 2 years. It was 2003, I think. Yeah, in 2003. So we waited 2 years, and we actually started. It's a prolonged testing period. It's not just a simple, hey, you go in and you do or you don't, right? So this isn't a simple blood test. You do psychological evaluation as well, because people have been known to commit suicide when they get results from something like this. Or there was a case where a woman nursed her mother through the end stages of Huntington's, and it just completely wrecked her enough that once her mother died, she killed herself, and she shot her 2 daughters as well, because she was just sure that they all had it. And if that weren't awful enough, and of course it absolutely is awful enough, one of the children actually lived and one died. The one that died didn't have it, and the one that lived did. And so, just absolutely horrible, horrible things associated with this disease. It is a horrible disease. Anyway, and so we decided we weren't playing that game. We weren't going to have kids who then had to make the decisions that we were currently having to make. And so if we had this, we weren't having kids. Well, I don't have the disease. But during that 2 years, God really used the whole situation to tell us that regardless of how the outcome happened, we were supposed to adopt kids. It was going to be part of our story. So as the result is, my brother and sister still haven't been tested. Both of them have children. One has 3, the other one has 2. And so our last question that we're actually going to take a look at is, well, what now? What does that mean with this diagram over here now that we know that I don't have it? Well, what it means is that the diagram has collapsed, right? The diagram no longer includes this first part at all, which means it doesn't include any of this at all either. It doesn't happen because I don't have it. The diagram actually becomes the bottom part. That's the only part of the diagram that now currently exists. So if we were looking at that diagram over here, we have the diagram that's just a 2-stage diagram. I won't rewrite all of it, but it's just a 2-stage diagram, much like the boy-girl diagram from the previous problem, with all the 0.5s everywhere. And you can ask yourself the same question, and you might feel like, well, at least one of you doesn't have it, so the probabilities should be much better now. So what is the probability that at least one of my siblings has it now? Well, you can calculate the probability the same way you did before. The probability that none of this has, or the probability that at least one of us has it, is 1 minus the probability that no one does. Well, the no one does probability is still this bottom branch, right? Just the only branch. It's the only branch that everybody came out, okay, basically. And that branch still had 2 0.5s on it, right? So what's 0.5 times 0.5? It is 1 minus 0.25, leaving me with number is really still high. It is. There's a 75% chance that one of my siblings does have it. And if they do, of course, then they each have their own children who could create their own tree diagram and look at it in the exact same way. So I present this question specifically because I want you to see that, math, interweaves into various aspects of your life all the time. But God's still in control. So this is an absolutely horrible disease. Absolutely hate that it took my dad's life so young. He was a very active man, and he was gone. He's been gone 6 years now. But this was what God used anyway to open our hearts and our minds to the idea of adopting children. And as a result, of course, you guys have seen pictures of my family before, back on the first day of class, and some of you a couple of different times than that. We actually have 6 kids, and only one of them is a bio kid, and that was a choice that we made. We made the choice that we were going to adopt as the way to grow our family, because that's what God told us to do. And so we've thought we were done at different points, and God said, nope, you're not. You just thought you were. So we've tried to stop telling him no, because that doesn't seem to be working very well. Anyway, so I usually pause before I do group work right here and just ask if you guys have any questions about any of this, because it's kind of a unique thing. Well, if you think of anything, I'm willing to share. We have group work on this section, and I'm not going to lie, this homework and this group work is probably one of the most challenging you're going to do because tree diagrams are a little bit complicated. So go ahead and take the next, we've got almost 20 minutes, about 18, and take a look at the group work for section 9.2. And I'm filtering around to answer questions as you do.